Previously, we've looked at how to formulate a problem as a linear programming problem. We're now going to look at how to solve it by plotting the constraints on a grid and using the objective line to maximise or minimise the function. First, we're going to recap how to show a region on a graph. We're going to show the region that satisfies all the points where y is less than or equal to 2x plus 5. So the first thing we're going to do is we're going to plot the line y equals 2x plus 5. This can be done by using the gradients and the y-intercept, or by substituting in points and joining them together to make a straight line. So that is the line y equals 2x plus 5. We're now going to select a point on either side of the line. So we're going to select minus 1, 1, but you could select any point. The origin is often an easy one to pick. If we substitute in x equals minus 1 and y equals 1, we arrive at 1 is less than or equal to 3. We now need to consider, is this true? And the answer is yes. So the point we have selected is on the side that is true for that inequality. In this case, we always shade the side that is false. That is because if we keep shading the sides that are false, eventually we'll be left with a region in the middle that is true for all inequalities. So we're going to shade the false side. If our point had been false, we would have shaded the side that our point lied on. Now pause the slide and use the handout to show the region that satisfies each of these inequalities. In each case, start by drawing the line. So for example, x plus 3y equals 15. Then select a point on either side of the line. Determine whether that point is on the side that is true or false, and shade in the false side. You may find that it's easier to plot the line by substituting in, for example, x equals 0 to find where it crosses the y-axis, and substituting in y equals 0 to find out where it crosses the x-axis, and then joining those 2 points together. So the first line, x plus 3y equals 15, we then shade the side that is false. The second line, 2x plus 3y equals 18, again shade the side that is false. The third line, 2x plus y equals 12, shading the false side. We're now going to draw the line x equals 0 and shade the side where x is less than 0. And finally, the line y equals 1, and we're going to shade the side where y is less than 1. So we are left with the unshaded region in the middle. This is known as the feasible region. We're now going to return to a problem that we formulated last lesson. So the constraints that we got from here are given there. And the objective function was to maximise p. Remember that the inequalities were called the constraints, and the line that we were trying to maximise or minimise is known as the objective function. In this case, we're trying to maximise because we're trying to maximise the earnings. So we're now going to find the feasible region, which is the region that satisfies all 5 of the constraints we found on the previous slide. So first, we have x is greater than or equal to 3. We've shaded the false side. We then have y is greater than or equal to 3, again shading the false side. X plus y is greater than or equal to 8. 3x plus 4y is less than or equal to 45. And 4x plus 9y is less than or equal to 84. So the region that is left unshaded in the middle is known as the feasible region. Any point in this region could potentially be a solution to this problem, and we are trying to maximise the profit while still remaining in that region. We now want to consider how many integer solutions lie within the feasible region, because sometimes it makes sense for x and y to take integer values only. So each point within the feasible region represents a potential solution, and each of those points there represent the points where x and y are both integers. In this case, it makes sense because the number of toes does need to be a positive integer. So there are 28 different solutions potentially in this region. We want to know which one would maximise the profits. So we could try all of these manually by substituting the x and the y coordinates into the objective function p equals 40x plus 70y. This would take a while, but we would find the point that maximised p, in this case, would be the point where x equaled 7 and y equaled 6, which is shown on the feasible region there. The value of p when x is 7 and y is 6 gives us a value of 700. There is a more efficient way of maximising the objective function. This can be done by plotting a line that has the same gradient as the objective function and then finding the highest value that it can take. So in order to plot the objective function p equals 40x plus 70y, we need to first of all choose values for p that are divisible by 40 and 70. This is just to make the plotting simpler. So for example, you may choose 140 as that's divisible by 40 and 70. You may choose 280, you may choose 560, and so on. All of those lines would give us the same objective function but at different heights. So to plot 140 equals 40x plus 70y, we could start by substituting in x equals 0 to find out where it crosses the y-axis, substituting in y equals 0 to find out where it crosses the x-axis, and here we'll be given the line 140 equals 40 plus 70y. We could have done the same thing, but with p equaling 280. This would have given us a slightly higher line, but with the same gradients. Or again, we could have chosen 560. So the idea here is that any of those lines with that gradient will be an objective function. Because we are trying to maximise the value, we now need to slide the line up as high as it will go before it leaves the feasible region. This can easily be achieved using a ruler. So we're going to move the ruler up now, being careful not to change the gradients until we reach the highest point. Now, because we were looking for integer values, we need to stop when the line reaches its last integer value. That gives us our solution of x is 7, y is 6. And substituting in x is 7, y is 6 into p gives us the value of 700, which we arrived at earlier. If the problem doesn't require x and y to have integer values, then sometimes the maximum value can be slightly higher. So in this case, we could continue to slide the objective function up until we reach the top vertex there. That vertex is maybe slightly more difficult to find, but we can do it by intersecting the two lines that form that vertex. In this case, the two lines that form that vertex are 4x plus 9y equals 84 and 3x plus 4y equals 45. So solving these as simultaneous equations will give us non-integer values of x and y. 69 over 11 for x, 72 over 11 for y, and substituting those into the formula for p gives us a slightly higher value of just over 709. Now going to practice using the objective function to either maximise or minimise. So for each of these questions, use the feasible region on the handout. For the first 6, you need to maximise each of the values. So in each case, these will be p equals, so p equals x plus 3y, and so on. For the 7th one, you're going to maximise but only consider integer solutions. And for the final 2, you're going to minimise the objective function, which means rather than having the ruler as high as possible, we are making the ruler as low as possible. So first of all, this is the line p equals x. We've arbitrarily chosen x equals 6 as a value there. And we can see that the largest that x can become is x equals just over 10, actually 10.5, We can find that by intersecting the two lines that cross there. For the second one, we're going to draw p equals x plus 3y. We have arbitrarily chosen 9 as a value of p. That is the gradient of the line, and now because we want to maximise it, we're going to keep the gradient the same and move the line as high as possible. We see that the last point before the ruler leaves the feasible region is there, and intersecting the two lines that create that vertex gives us an answer of 29. That is coming from x equals 2, y equals 9. For the third one, we're going to draw p equals y plus 4x. We've arbitrarily chosen p to be 8 in order to get the gradient correct, so y plus 4x equals 8. We then need to raise the line as high as possible, and we can see that the point there, x is 10.5, y is 1, giving us a solution, a maximum solution of 43 for p. For number 4, we've selected 10 arbitrarily as the point value for p. That is because 10 is divisible by both 2 and 2.5. Having got the gradient of the line, we can then maximise, and we arrive at the vertex where x is 9 and y is 4. Substituting that in gives us 30.5 as our value for p. Next, we're going to plot p equals x plus y. That is the line x plus y equals 8. And the highest that line can arrive at. Now in this situation, because the line has the same gradient as the last line that it meets before it leaves the objective, the feasible region, there isn't just one single point, one single vertex, which gives us a maximum. We actually have any point along that section of line. So any point, any pair of coordinates starting from x is 6, y is 7, and continuing along until we get to x is 9, y is 4, any of those points should give us the same maximum. The maximum that we get from that is always 13. Okay, the next line, we have y minus 2x, and we've arbitrarily chosen 2 as the number, the value for p. So that is the line y equals minus 2x equals 2. The easiest way to draw that line would be to rearrange it to make it y equals 2x plus 2, and then draw it with a gradient of 2. This time, the highest that line can travel gives us a solution of x equals 0, y equals 9. So the maximum value is 9. Next, we're going to maximise y plus 5x, and we're going to only consider integer solutions. So we'll start by plotting a line p equals y plus 5x. In this case, we have p is 10, so y plus 5x is 10. So you can see that the maximum integer solution is slightly before the maximum solution here. So we have x is 10, y is 2 is the maximum value while still considering integers only. So if x is 10, y is 2, the solution we get is 52. Finally, for the last two, we're going to minimise, first of all, y plus x. So we're going to draw the line p equals y plus x. That is the line x plus y is 8. This time we want to minimise, which means the line needs to be as low as possible. The minimum value there is found when x is 0 and y is 1. So the minimum we will get is 1. Finally, to minimise y minus 2x, we're going to start with the line y minus 2x equals 2. To minimise it as far as possible, we arrive at this vertex here where x is 10.5, y is 1, so the minimum value is negative 20.